Hey guys, today we're going to talk about arcs and chords in a circle. We're really going to go over three main theorems, and I'll explain those theorems and we'll go through the proofs of those theorems as well. So whenever you have a circle and you take a chord on the circle, so if we have a circle here, and you take a chord, we'll call it circle C, any chord that's not the diameter, so we take AB, any chord that's not the diameter, it's going to divide the circle into two arcs. Your minor arc, AB, and we'll call it the major arc, ADB. So you have the major arc and the minor arc. We're going to focus on the relationship between like this chord and its minor arc, and how it relates to other chords within the same circle, or within a congruent circle, which essentially is like working with the same circle. Okay, so the first theorem we're going to look at, and if you're using your book to follow along, this is page 715. Our first theorem states that in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. An example we have looks like this. We have circle L, and we're given the chord JH, and we're given the chord FG. FG. And what this theorem is saying, there's really two ways to think about it. We have an if and only if there. So we have, let's say we know our arcs are congruent. So, given that, then actually I'm not even going to say this. Given that FG is congruent to JH, these arcs, that is true if and only if the segments, or the chords really, are congruent as well. So if we know the arcs are congruent, then we know the chords are congruent as well, and it works the other way as well. If we know that this segment is congruent to this segment, if we know the chord FG is congruent to the chord JH, then we know their arcs are going to be congruent as well. And we're going to go through the proof of this. So it's really, you need to prove two cases for this. So the first one, I'll write out for you your givens and what you're trying to prove. You can try it on your own. There's a nice step-by-step you can check with, but we'll prove the other way together. So the first one, and we'll use the same diagram for both. Here's our circle. We have circle P, and we're going to have chord QR and the chord ST down here. And the first one, this one you're going to try on your own. You can check with the proof in the book to see how you're doing. We're given, obviously, circle P, and you are given that the arc QR is congruent to the arc ST, and you're trying to prove that the segments, or the chords, are going to be congruent as well. So chord QR will be congruent to the chord ST. And you can go through the proof of this on your own, try it out. You can follow along with the step-by-step right on in the book. We're going to prove that instead of given that the arcs are congruent, we're going to be given that the chords are congruent and prove that the arcs are congruent. So instead of given this piece of information, we're going to be given that QR is congruent to ST, those two chords, and we're going to try to prove that the two arcs are congruent. So QR would be congruent to arc ST. Alright, so you can try to map this out on your own if you want, and then we can come back together. You can pause the video, feel free, try to do this proof on your own. I'm going to go through it right now though. So, we're going to do a little two-column. We'll have statements and reasons. So the first thing we should state, well, it's our given information. We know that we have circle P, and we know that we have the two chords, QR is congruent to ST. We know this. And let's think of some other things that we know with circles. Well, with circles, any point that lies on the circle is the same distance from the center. We call that the radius. So all of these segments are all going to be congruent because they all represent the radius. So from that knowledge, we know that, well, SP, it's a P in the middle, so SP is congruent to TP, which is congruent to QP, which is congruent to RP. And we know this because in a circle, radii are congruent. So radii are congruent in the same circle. And we're clearly in the same circle here. Alright, so our next then, if we look at what we've created here, well, clearly we have 3 pairs of congruent sides, so we should be able to tell that we have 2 congruent triangles. Triangle STP, and I'll say corresponds with triangle QPR. The S and the T and the Q and the R, since it's isosceles, those could have been switched, but the P needs to correspond with the P here. And we know this, well, because of side, side, side. And once we know this, we'll keep in mind what we're trying to prove. We're trying to prove that arc QR is congruent to arc ST. So we're trying to prove that QR is congruent to ST. In order to do that, we're going to need the central angles. So we're going to need this central angle here and this central angle here. Well, we can show that they're congruent because, well, CP/CTC. With these 2 triangles being congruent, we know that angle SPT is congruent to angle QPR. And by those 2 being congruent by CP/CTC, well, we can conclude from there, therefore our arcs, what we're trying to prove, QR, is congruent to arc ST, and we know that because, well, in the same in the same circle, 2 arcs are congruent if their central angles are congruent. So since arc QR, its central angle that made it, is going to be congruent to SPT here, that means ST and QR are going to be congruent. Alright, and that's our first proof of the day. Our next theorem that we're going to talk about, our next 2 actually are very similarly related to each other. The first one, it says, and I'll draw the picture first so we can describe as we go. Here's our circle. We're given circle C. We're given AB going across, and we're given XY going here, given point Z, and we're given that this is a right angle. So this theorem states that if the diameter or radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. So looking at what we have here, and this is a B over here, given that our diameter, AB is the diameter here, given that AB is perpendicular to this chord XY, we know that, this is what this theorem is saying, we know that it's going to bisect this chord, so these 2 segments are going to be congruent, and we also know that the arcs are going to be congruent as well. Now we're going to need to prove this, then we can use it. So given, and we'll use this circle as an example here, so given, well, we have circle C, and we are given that AB, our diameter, bisects XY, and we are trying to prove that XY is congruent to ZX, or sorry, ZY or YZ, what we marked off here, and we're also trying to prove that the arc XB is congruent to the arc BY. So this is everything that we're trying to prove. Trying to prove 2 things here for this theorem. So let's start off with what we know, and we'll make a little table, a T table. our given information, well, it's right up here. We have circle C, and we know AB is perpendicular to XY. So if you want to try to map this proof out on your own, that's a good idea, and see if we agree and get there in the same steps. So, some of the things that we should think about with this. How are we going to prove that these two segments are congruent? Well, one of the things that we should know, because these are perpendicular lines, AB is perpendicular to XY here, these two segments are perpendicular, we should know we're going to have 4 right angles, and we can use that. If we know that all these are right angles, and we know, well, we can use the radius, the radii here, we would have right angles, we would know each radius is congruent to one another, and then we can use a little reflexive property here, and we're going to create 2 right triangles, and then we will by CP/CTC show those 2 segments are congruent. So we just need to go through all these steps. So our first statement that I would make here is saying that angle CZY, and also angle CZX, well, they are right angles. And we know that by the definition of perpendicular lines, in this case segments. So we know we have those 2 right angles. We also know that CX should be congruent to CY, and that's because in a circle, within like the same circle, the radius is going to, or all the radii are going to be congruent. So radii are congruent. Then, so now we're close. We have this, we have all the angles. We also should know CZ is congruent to CZ. That would be our reflexive property. And then from there, well, we have 2 right triangles. So we know triangle CZY and triangle CZX. We know they're right triangles. That's the definition of a right triangle. And then if you look, now we didn't know these were congruent, so I'm going to take the markings away. We're trying to prove those were congruent. But from what we do have, well, we have right angles, and if you look at both the triangles, we have a hypotenuse and a leg. So we have triangle CZY is congruent to triangle CZX, and that would be by your HL theorem. And then through CP/CTC, we can say these 2 segments are congruent. So XZ would be congruent to YZ, and that would be because of CP/CTC. Now we've proven half of what we want to prove. We also need to prove that the arcs are going to be congruent as well. So in order to prove this, well, let's think of how we can show that 2 arcs are congruent to each other. And we don't know that they are, so we'll take them away. But to show that 2 arcs are congruent, we need to show that their central angles are congruent. So if you look at arc XB here, its central angle would be right here. And if you look at arc BY, the central angle would be formed right here. So can we show that those 2 are congruent? Well, yeah, because we have 2 right triangles, and those are within the triangles. We also can say that, and I'm going to say it as angle XC, I'm going to say B. That angle is congruent to YCB. And that's from CP/CTC. I'm only using the B here instead of the Z just because maybe it'll help us see the arc that we have. So once we know those 2 angles are congruent, well, then we know that XB, that arc is going to be congruent to BY. And we know that because, well, when we have 2 arcs, they are congruent if their central angles are congruent. Central angles are congruent, so therefore the arcs are congruent as well. Alright, so that was our second theorem. Our next and final theorem of the day is very similar to this. I think the proof's a little easier. Here we go. So our next theorem, it states we have a circle, we have circle C, and then we have the diameter, actually a chord for now, AB, and we have this chord XY, and we know it's going to be bisected. So this says the perpendicular bisector of a chord is the diameter of the circle. So in this case, if we know that, well, XY is a chord, if we know that the chord AB is perpendicular and bisects XY here, then that chord AB is going to be the diameter of our circle. And we're going to go through the proof of this. So again, this theorem is telling us if we know that this chord AB is going to be the perpendicular bisector of another chord, then that chord is going to be the diameter here. So given, so can we prove that this is the diameter? So given a little information, well, we have triangle, I think this is triangle C here. Yes, triangle C, or circle C. We have circle C, and we are, let's see, given that AB is going to be perpendicular with XY, and we also know that XY is going to be, oh no, XZ, put a Z here, XZ is going to be congruent with YZ. We want to prove that AB is the diameter. So basically we're trying to prove, in order to prove this is the diameter, we know it's a chord, we have to prove that it goes through the center of the circle. And that's just basically saying that if you are going to be the perpendicular bisector, that means you're going to have to go through the center of the circle. That's what we're going to try to show here. Okay, so our givens are given to us, we know what we're trying to prove, so you can try to map this out, think of what you're going to use. And let's see, so we have circle C. Let's go ahead and make some statements and reasons. Well, we have our given information. Well, we know we have circle C. We know we have, well, AB is perpendicular to XY, and XZ is congruent to YZ. Cram this in. Really, AB is the perpendicular bisector of XY. That's what it means to be the perpendicular bisector. So from this information, well, let's think about what we know. So point C here, think of its relationship to, or what we know about point C. We know it's the center of the circle, and a way that we can use this is going to be that, well, point C is going to be the same distance away from X as it is away from Y, because the radius to any point on the outside of the circle is going to be the same. It's going to be the same, the segments are going to be congruent. So I'm going to say C is the same distance from X and Y. And we know this, well, the reason why we know it's the same distance is because, well, radii are congruent. So the fact that the radius is going to be congruent to any point means that C is the same distance away from, well, X and Y here. Now if we think back to perpendicular bisectors, because that's what AB is here, AB is the perpendicular bisector, well, point C we know is going to lie on the perpendicular bisector of XY. And the reason why we know that, well, if we go all the way back to our perpendicular bisector theorem, this would be the converse of the perpendicular bisector theorem. So we know that C lies on the perpendicular bisector of xy. And that's the converse of the perpendicular bisector theorem. And again, we know that AB is the perpendicular bisector, and since C falls on the perpendicular bisector, therefore that means AB goes through the center of the circle, which means AB is a chord going through the center of the circle, so AB is therefore your diameter, is the diameter of circle C. And we know this, well, that's what the definition of diameter is. And then we're all done. Alright, so that basically summarizes our 3 theorems of the day. Now that we know these 3 theorems, we've proven them, we can use them to find missing measurements. We can use them now whenever we're doing problems with circles. Alright, so go ahead and try a few problems on your own. Have a nice day, people.